Hello there. I wanted to take a few minutes and talk about inverse trig functions and how they're related to trig functions in the unit circle and all the other stuff we've been doing. So thanks for tuning in. Just a little bit of background. I think we're all pretty comfortable at this point when you're asked for sine of 30 degrees. You could either create a triangle that has a 30-degree angle. That triangle would look something like this. Or if you're comfortable with the shortcuts of the unit circle, the idea is that 30 degrees corresponds to this value of 1/2. And you can do that with any kind of nice angle, any reference angle that's a special angle. So if I did something like cosine of 240, well, that's associated with this piece on the unit circle, and cosine is that first value. So that's what we spent some time in class doing. So what I really want to talk about, though, is these inverse trig functions. First thing is just the way it's written, because it's kind of different at first. When you have this written, it's pronounced sine inverse of x. I know it looks like a -1, but it stands for inverse, sine inverse of x, cosine inverse of x, etc. And when you have an inverse function, what it does is it kind of works backwards. It balances out an equation. Back in the day, when you solved equations like this, I guess you still do, we talk about how we would subtract 2. Maybe we use the term opposite, but what we're really doing is the inverse of addition, and it causes things to balance out. So what we're going to do with the trig functions is a similar thing. It just looks a little bit gnarlier. So the way things are going to be written is if you have something like sine inverse, and then you're going to have a value in there. So if you're trying to solve for x, what is sine inverse of 1/2? So there's a couple ways to do this. One is just to realize what it's asking. And what this is asking is it's saying sine of what value is 1/2. So instead of having the output be your value, now the idea is you're trying to find the theta. You're trying to find the angle that spits out a 1/2. But notice that when I first opened up this video, we have this as a conclusion, and this is sine of 30 is 1/2. And so with this example, x is 30 degrees because that's the value that spits out a 1/2. Let's try another one and see if you can see it. If I said tangent, let's not do tangent yet. If I said cosine inverse of 1/2, and we were trying to find that. One way of thinking about it, and my little thought bubble here, thought bubble, there I am thinking, this is saying cosine of what value is 1/2. And if I look up here, cosine is 1/2 right there. And the value that it's talking about is 60 degrees. So a solution to this would be x equals 60. It's not a lot of work to show for these, but you got to know what right place to look. So we're essentially trying to find the values that the thetas, the angles that spit out these values on the inside. One other thing to add, and then I'll do a couple applications of this. One thing you might have noticed, when I say sine inverse of 1/2, maybe if you're looking or curious, we pointed at the fact that sine is 1/2 here. But check out this value, 150 degrees is also a solution. So x equals, 30 degrees, but x also equals 150. And, it's negative down here, so those aren't issues. But if you think about coterminal angles, you know, if I took 30 degrees and added 360 to it to get 390, that would also be a solution. And if I took 150 degrees and added 360 to it, you know, I get 510, I think, that would also be a solution. I mean, these are all values that would spit out 1/2. You can verify them in your calculator, right? Sine of 510 is going to spit out 1/2. And so sometimes on the book or the homework or Delta Math or whatever you're working on, it'll say, you know, solve this, but your answer should be, you know, in quadrant 2. You know, and then you got kind of narrowed it down. Or it'll say solve this. And then it'll give what's called a domain or a restriction. It'll say, but we want the x value between 90 and 180. And what that means is you've got a bunch of potential x values. In fact, this could keep going on forever if you keep adding 360s, right? Just like those coterminal angles. But if it gives a specific domain, then we want to find the value that falls within that domain. So again, not that hard, but definitely a few little details to watch out for. All right, a couple helpful facts about inverse functions, and these are more kind of application things. So let's say you're asked, or you think about this as kind of a solve equation. Let's say you have sine inverse, we'll go negative 1/2 equals, you know, theta, or equals x, or whatever you want to do. Let's say you don't, you want to have like a specific way to solve this. You want to use math and symbols to isolate, you know, to get an answer here. And so, one thing you can do, and an analogy was with you know, something like this. When you're thinking about getting rid of a square, a lot of people say, well, you can square root both sides. You've learned over the last, you know, years that square and square root are related. And what they technically are their inverses. And that's why when you do that, it's technically plus or minus 2. That's why you can get x by itself. And so if you have a sine here, or a sine inverse, and it's kind of weird to think about it, but if you sine both sides as an operation, just like the square and the square root canceled out over here, that's what the sine and the sine inverse do. They cancel out and it becomes this. And so now it's a little bit easier to see, okay, what value, you know, what value of theta gives me negative 1/2. That's what this question is really asking. So that's absolutely appropriate to write it that way. Sine is negative 1/2 right here. Sine's negative 1/2 right here. So if we want to have a couple solutions, 210 is one solution, and 330 is another. And then we'd have a bunch more solutions if we needed them. All right, one last thing here. You guys have been very patient, assuming you're still watching. The one last thing too is this. Let's say you have a triangle problem. It's a crooked triangle. Let's say it's a right triangle. Let's say we have a theta, and then I don't know. Let's say we have a 5 and a 4. And the question is solve for theta. So going back to SOHCAHTOA, our standard, think about how you could set up a trig ratio with the theta and the 5 and the 4. So when I look at this, I realize that I have an opposite side to theta, and I have an adjacent side to theta. And so when I think about SOHCAHTOA, I try to think about which uses the opposite and the adjacent, and TOA comes to me. And so this, one way I could write this is tangent of theta is, we know it's opposite over adjacent. That's just a definition. But according to this picture, I could say it's 5 over 4. And so now if I actually wanted to solve for theta, this is where the inverse comes in. This is not a value on the unit circle, and that's where I'd have to use technology. And so using this idea up here, everybody, watch the magic. If I tangent inverse both sides, the tangent inverse of the tangent cancels out, just like a square and a square root, just like a plus and a minus. But over here I have tangent inverse of 5/4. Unfortunately, I don't have a calculator nearby, but this is something, there's a button dedicated to it. Do tangent inverse button and then put in 5/4, and that will give you your answer, which is the angle that would be part of that triangle. So there's two little applications. I promise you the notation is a lot scarier than it is, especially in the sense that if you can get to the end, you're going to use technology to help you out. So thanks for watching, guys. As always, bring questions, and I'll see you guys soon.